And we're live.
Ooh, I know, it's exciting. All right, so here we go. All right, so we're going to learn today about drag force. Ooh, I'm going to go single screen. Look at that. All right, so last year, and this year for that matter, we learned that if you drop an object, it eventually reaches terminal velocity, right? So somebody tell me real quick, why does that happen? Sure, we got it.
Because the force of gravity equals the force of air resistance.
Good. So eventually you get to a point where gravity's pulling it down, and the air resistance cancels that out. Tell me a little bit more about how we get to there, Gianna.
When it's falling through the force of gravity, when it speeds up as the velocity increases, the drag force increases.
Good. There you go. The air resistance, which we're going to begin calling drag force, depends on the speed, right? The faster you go, the more air resistance there is, right? Okay, and this is true of any fluid, whether you're walking through air or water or helium or whatever, that's always going to be true, right? And that's why if I fancy sunglasses, Renee? All right, so that's why if I move this paper slowly, it moves a little bit, right? But if I move it quickly, it moves a lot more, right? More drag force pushes the paper up farther, right? That did not translate well to the video, so you'll have to get that picture in your head. All right, so is everybody cool with that idea? Yes. You go faster, more air resistance, all right? All right, so I guess I should just make a note here. All right, so terminal velocity occurs when the drag force is big enough to make your net force 0. Okay, so your terminal velocity occurs when your drag force gets big enough to make the net force 0. That is not how you spell enough. All right, now the reason I didn't explicitly just say FG equals FD is because theoretically you could have a situation where you've got like a thing on an inclined plane and you reach terminal velocity, right? Or, well, that would still be, yeah. All right, but do you guys see what I'm saying? So it might not necessarily always be exactly the force of gravity that's producing the acceleration. Okay? You know, maybe you've got a jet with rocket boosters, and those rocket boosters are pushing it forwards. And as it speeds up, the air resistance pushes it back. You know what I mean? Clear? Excellent, horrific. Okay, so the first year, I'm going to plow through this slide. You do not need to write most of this down. Okay, so the first year I taught this, I got all my drag force notes from the book, and the book gives this ridiculous equation for drag force. Okay, so it turns out that the drag force on an object depends on these things. It depends on the fluid density, rho. Okay, so that's the density of the air or water or whatever the object is moving through. The cross-sectional area of the object, right? Like if I do this, that's a lot more air resistance than if I do this, right? Okay, so the cross-sectional area matters. Here's the important one, the velocity relative to the fluid, right? The faster you go, the more air resistance there is. And then this last thing, an experimentally determined drag coefficient, similar to like a coefficient of friction, basically. All right, that depends on the shape of the object. Okay, right? Aerodynamics, something pointy is going to have a low drag coefficient. A parachute is going to have a high drag coefficient. Cool? All right, so my first year, I gave a bunch of problems where I had to use this equation, but I've never seen it on the AP test. All right? So usually the way the problems are worded on the AP test is they tell you, okay, well, the drag force depends on the velocity, and then there's some constant, and they just give you a constant. Okay? Does that kind of make sense? All right. It's rho. It's the Greek letter rho. Sorry, these are supposed to be the same symbol. I just did a crap job of making my rho symbol up here. The density.
Where's Wade?
Sorry?
Where's Wade?
Oh, good. Very good. I got you. He's jailed, right? I don't know. Did he win or lose? I don't know.
I don't know.
All right. All right. So, on the AP test, so this is the important part. On the AP test, the way most of these problems will be worded is your drag force is going to depend on your velocity, and so either the drag force will be proportional to the velocity squared, Or sometimes they give you an even simpler version and they say the drag force is proportional to the velocity. Follow? All right, but so the idea here is the reason this becomes confusing is because now we've got a non-constant force. All right, the only other force we've dealt with this year that was non-constant was friction's usually constant. Springs, right? Spring, right? Okay, but there the force doesn't depend on the velocity; it depends on how far the spring is stretched, right? Here, the force depends on the velocity, so this gets really complicated because as your force changes, your acceleration changes, which changes the velocity, and as your and it snowballs, right?
Yeah.
Okay. So anyway, they'll give you this constant k, and that k depends on all this other garbage up here, the coefficient, the density, the surface area, blah 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 blah. All right, everybody good? Okay. So the reason I don't love this is in the same way that those coefficients of friction are experimentally determined, this coefficient is experimentally determined, so they're never 100% accurate anyway. So really, just going to this option is probably a little more accurate anyway, which is why I think the AP test opts to give the problems that way. All right, so I want to, if we're going to get through at least one example, my goal is to get through 3. We'll probably land somewhere in the middle. Okay? So, all right, so write this example down. I will read it. All right, so an astronaut in a space station. All right, so he's in a space station. There's air in the space station, but for all intents and purposes, we can treat him as weightless, right? Follow? So that's why I put him. So the only force here is going to be air resistance, drag force. Okay, so we've got this astronaut in a space station. He's going to throw an apple that has a mass of m to another astronaut. He releases the apple with a speed of v0. That's what we usually call vi, if you care. If you want to use vi instead of v0, you can. If the only force on the apple is the air resistance, and here's the equation for your drag force. I used b instead of k, just to show you that the letter that we use is irrelevant. Okay, so our drag force is equal to negative b times v, where b is some positive constant. And then there's a bunch of constants. And these model the way that they're usually written on the AP test. That first one, if you take up.
Was there one last year?
Don't remember. I don't think so. Which leads me to believe more likely that it would be this year. And once you guys figure these out, you guys will be fine. This first example does have one thing that's particularly challenging, but you'll see. You'll be okay. I am confident. So Renee, this is not a loaded question. Does that work for you, just taking pictures instead of writing it down?
No, I'm writing it down. I'm just like behind.
Oh, I gotcha. You can tell me to wait.
No,
It's for Snapchat.
And I did intend to print these for you, but the printer was being uncooperative.
Wait, you write 1 through 5 down?
Yeah, I guess so. Yeah, I mean, if you're done writing the first part down, I'd write down the other questions.
space by me for part.
Mr. Ecker?
Just jam them all together and then number them as you solve them. You'll be okay. Yes, Sean.
Are you ever afraid that someone's going to take all of your videos and merge them to make a sort of like voice speaker? Because I
Worried?
thought about doing that.
Worried or excited? I just get some of the royalties, please. Like when they do the news mashups, is that what you're talking about?
Yeah.
Like the opening to that show. What do you got? No, not SNL. The show with the girl. She lived in a bunker for a while.
No.
Kimmy Schmidt. There you go. Yeah, like the beginning of that, right? I know what I'm talking about. Frasier. That's it. Rory Calhoun.
Are you
This is such
reading
an
it
awkward
all already?
I guess I can pause the
Right,
video. You know what? I'm gonna leave it because otherwise I'll forget to unpause it.
oh my
Those of you at home, I'm sorry.
Gotta give him a time stamp.
Yesterday? Just like in the video, like put
That
like
was
a
not a sentence I expected to hear today, John Kyle.
Huh?
That was not a sentence I expected to hear today. Yesterday in math class, I drew the coolest beaver. That was the sentence I just heard.
Oh, wait, you're on a beaver now?
Yes, sir.
Just in the video, put like
Careful. Okay, go ahead.
put like a skip forward to this time to continue.
Yeah, could do that on YouTube.
Yeah.
It's
Time stamp.
not really. I'll do it for. I'll do it in the
I want to like
comments.
wipe right push one and solve it, and then right.
You're gonna have to just get over it. All right.
I already got this.
Is everybody good? Everybody got it written down?
Yes.
Or at least enough that I can move forward.
Yeah.
All right, so all of these problems begin the same way. I'm going to say it again because it's super important. All of these problems begin the same way. Anytime you've got a problem that deals with drag force, you're going to start with net force equals net force. Okay? Now, how do I want to do this? Oh, dual page. You gotta make sounds or it doesn't work. All right, so here we go. A, right, but do not solve a differential equation which could be solved to find the velocity of the apple. Oh, wow.
Wow.
All right.
If they gave you a master's.
All right, so here we go. So net force equals net force. So really you'd want to make a free body diagram. For this one, there's not much to it. John, that was funny. Here's your velocity. So what forces are acting on it? This is the drag force, the air resistance. Point for me. Which way? It resists the motion, right? It drags the thing back. So here's my drag force. So net force equals net force becomes mass times acceleration equals, in this one, it's just drag force. Okay? Bless you. So I'm going to make two substitutions. When I said every problem begins the same way, this is what I'm talking about. I'm going to replace acceleration with dv dt. What does that mean in English? It's the derivative of velocity, right? Velocity is the derivative, sorry, acceleration is the derivative of velocity, right? And the reason I'm doing that is because I know my drag force depends on the velocity. So I'm going to replace drag force with negative b times v. Remember, b is just some random number. It's a fixed, constant number. All right? Now, eventually, you guys will take Calc 3, which is what this is. All right? It's called differential equations. All right? And a couple of the Calc 3 students were asking me this. They were like, what's a differential equation? I was like, I don't know. I gotta look it up. This is a differential equation. A differential equation is an equation where the value of the derivative depends on the thing you're taking a derivative of. Right? So in other words, the rate at which the velocity changes depends on the velocity. I won't say that because I'm recording, but boo, right? Like that's a pain in the tuchus. All right? So we got to figure out a way to solve it. And the process is always the same, and I will tell you that process as soon as I answer Sean Gates' related question.
Well, isn't that every derivative though? Isn't it always dependent on what you
No. So usually what you'll have is like the velocity at time t is whatever, 4t plus 7, right? And then when you take the derivative, you're not taking the, like, it's just 4, right?
Yeah.
So that was a crappy example. Here, let me do that. So here, the derivative of the velocity with respect to time doesn't depend at all on what the velocity is.
Depends on time.
It depends on the time, exactly. Clear?
Wait, how did you know to place it? Oh, because FD is going to be V.
Yes. All right, so is everybody good up to here? All right, so again, so Question 1, write a differential equation which could be solved to find the velocity. This is it. That's the answer to number 1.
We have to rearrange it at all?
Eventually, yes. But here, if it says write but do not solve, you're done there. Once you've got derivative equals a thing, you're good.
Grand.
All right?
Oh, that's
So on an AP test, this would be 2 or 3 points. Probably 2 on this one because there's not much to it. But good? All right, so now the solving it part. And this is usually how it will be set up is question 2 will be now solve the equation. I'm trying to break it up into steps to kind of guide you through the problem. Okay? So most of you have never solved one of these. The process is always the same. All right, what you're going to do is you're going to get all of your V's and dV's on one side and everything else on the other side. Okay, so weirdly, you're going to multiply by dt, which seems a little weird, but just remember, dt is just like a really small amount of time. And then dv is the corresponding change in velocity for that really small change in time. Follow? Okay, so I'm now on to number 2. So I'm going to multiply both sides by dt to get m dv equals negative bv dt. Now, my strong recommendation is move all of your constants to the dt. Sorry, try that again. Move all of the constants to the dt side, and anything else goes on the dv side. Cool?
I say that again.
Move anything that is as best as you can. It won't always be 100% possible. But as much as you can, move any constants to the dt side of the equation. And then whatever you can't move stays on the dv side. Follow? All right, so what I'm going to do is I'm going to get my v's and dv's on one side, and then constants and t's on the dt side. Does that make sense? Adrian? Oh, okay. Yeah, it's good to wave at people. All right, so here we go. So I'm going to rearrange this. So this becomes dv over v, right? I divided both sides by v to get the v and the dv on the same side of the equation. M is a constant. I don't like it on this side. I'm going to move it to the dt side. So I get negative b over m dt. All right? Now, it will never happen here in physics, but just so that you know, in math, if you ever had a t, like just a variable t, you would want the t on the dt side. The way these problems are set up, there won't ever be a t, so it doesn't really matter. All right, everybody good up to there?
So, wait, does that mean that we're never going to be given an equation for the velocity to quit?
Correct.
Okay.
In fact, that's what we're trying to find.
Oh, right.
That wasn't. I know this is your first exposure to it, so I get it. But that's our goal, you guys. So to bring us back to base, what are we trying to do? We are trying to rearrange this garbage so we can figure out an expression for the velocity as a function of time. That's what we're trying to find.
Right.
Okay, Michael?
Why are you doing dv over v versus v over dv? Velocity and side.
What do you do?
Last step.
Yeah, no, I know, but I mean, so, well,
Is there a reason?
you'd have to flip both sides over, and you'd have v over dv on this side, and over here you'd have, what, negative m over b dt? But your dv's and dt's would be on the denominator of the fraction, which doesn't make sense for our next step. So let me go one more step, and I think you'll see why. Okay? So long story short, you want your dv's and dt's on the top of the fraction elements. Okay? Everybody good? John, Kyle, you good? Okay, you gotta be less distracting today, please. We have a lot to get through. Okay? All right, is everybody good? All right, cool. So now what I'm going to do is I'm going to take this mess and I'm going to integrate both sides of it. All right, so I'm going to rewrite the exact same expression, but I'm going to stick a little integral sign in front of it. Oops. Except I'm going to do it the right way instead of the wrong way. So dv over v equals negative b over m dt. And I'm going to put an integral sign here and here. Why did I put it there for the dt? Because the b over m is constant, so it doesn't affect anything, right? All right, now here's the super. You good, Adriana?
I think so. All right, keep going.
Okay. Any problems?
No.
I don't know why I keep doing this today. Hold on for a second. Okay, so now, here's the deal. So now, our bounds of integration. This is the super important part of this. Okay. So the bounds of integration are the super important part. So the question wants us to figure out, at the end of time t, what's the velocity, right? So what I'm going to do is, on this side, I'm going to integrate from 0 to the end of time t. And on the other side, I'm going to choose the corresponding velocities. So at time 0, what was my velocity? V naught, right?
Not zero.
And at the end of time t, my velocity is v of t. You could also just call it vf if you want. But I'm calling it v of t because I want you guys to understand that we are solving for the value of the function at time t. Say that again?
Would that just be like any other v of t equation that we've used?
Sure, yeah, that's what we're trying to find, is what that equation is. So our goal now is we're going to use a bunch of calculus and garbage to solve for this upper bound. Like, that's the thing we're trying to find, is what this dude up here is. Follow? All right. So, quick calculus crash course. What's the integral of t squared dt? 1/3 t cubed plus c. Yeah, but we're doing definite integrals, so I'm not going to worry about the plus c. All right. What's the integral of t dt?
T squared over
1/2 t squared. What's the integral of dt? T. Oops, I forgot my pants. Does that make sense? Oh, so this whole mess here just becomes t. Oh, I'm waiting.
Just like,
Here.
I need to see it, and you're in the way.
Oh, I got you. Sorry. We gotta move your t.
No, no.
Don't, and shh.
Nice. Goodness.
I'm just kidding.
Wait, how did you get t squared dt?
Where? Here?
Yeah.
I was just saying, this is a quick calculus crash course. I'm just showing you.
Oh, I
The
thought
integral of t squared is this. Integral of t is this. Integral of dt is
Oh,
t. That was
I
the
thought-
whole point of this.
I thought that was part of the problem.
Nope, that's why I did it. Yeah. Side note. All right, so is everybody good with that? Integral of dt is t.
Yes.
Good? Cool. So this guy here becomes, the right side of this equation is negative b over m times t, right? Now, the left side of the equation is a little bit uglier.
Yeah.
So,
Natural.
okay, so do you guys know that the integral of 1 over x is natural log of x?
We do in BC.
Is that is AB students, talk to me. Nate, I'm going to pick on you again. I'm sorry. I hope you don't mind that I keep using you as my guinea pig. Is that a thing you've learned? That the derivative of 1 over x is natural log of x?
A while ago.
A while ago. Okay, so it's a thing you've seen. All right. So, those of you to whom this is not familiar, make a note of this, that the integral of 1 over v dv is the natural log of v.
Does the absolute value matter there? Or no?
There is no, where do you see an absolute value?
It's the natural log of the absolute value.
Oh, gotcha. Is that true?
It is. The original domain.
Oh, right. Okay, yes.
So you don't have to worry about
Gotcha. Okay, no, the absolute value is not an issue.
Cool.
All right, good. I think that's the only count, like the only derivative you may not have been familiar with. All right, so real quick, well, we'll get there in the next example. Okay, so everybody good with that? All right, so all you missed was just the derivative of.
It's fine.
All right, so this becomes the natural log of v evaluated between v naught and v of t. Oh, it's not going to do it. Oh.
It's gonna.
Ooh, it worked. Phew. Okay, everybody got that? Nate, you good?
Good.
Everybody happy? Would you tell me if you weren't, Nate?
Yeah.
Cool. All right, so here we go. So now all I got to do is I got to plug in my bounds, right? So remember, it's always top minus bottom. So this becomes the natural log of v of t minus the natural log of v naught. And that equals negative bt over m. Everybody good? All right, so quick refresher in logarithms. You're welcome.
Yay.
Aren't you guys excited? This is like the best unit ever. Logarithms, calculus. All right, so here are two log properties you need to know. You should know that the natural log of A plus the natural log of B is the natural log of AB. That comes up occasionally. What comes up more often is this guy. The natural log of A minus the natural log of B is the natural log of A over B. You're going to use that a lot. While we're talking about general log properties, a couple other quick things.
Nice. Now you're fine now.
Let's see. You guys all know that if you've got an equation that has a natural log, you can rewrite it as a e to the equation and vice versa. So real quick, here's how that works. So if you're given an equation that looks like this, the natural log of x equals y, for example, if you raise both sides to the e power, e to the natural log of x is just x. Oops. Good? Is that a thing you guys all knew?
Yeah.
Okay, cool. And you guys know you can go the other way too? Now if we take the natural log of both sides of this, it'll get us back to here. Cool? All right, cool. Other stuff you might need is the power rule. I don't know if this will ever come up, but just natural log of A to any power P is the same as P. Oh yeah, well, not really. Cool enough. All right, finally, what's the natural log of E?
1.
1. What's anything to the 0 power?
1.
1. Cool. So those are some quick things that you're going to need. Ooh, I'm going to answer my phone while you guys store that away in your brain. Hello, this is Mr. Hacker. Prank caller!
What?
Somebody breathing really heavily. All right. All right.
So if you get some random call like seconds later, I'm just gonna be like,
All right. All right. Is everybody good up to here? All right. So I'm sorry. A lot of distractions. So let's rewind. So here's where we're at. So we had this mess, right? We got all of our v's and dv's on one side, constants, t's and dt's on the other. Integrate both sides. Please give careful consideration to your bounds. And then take your integral. Good? All right, now, what was our original goal? Well, we were trying to solve for v of t, right? So, there's a couple ways you can do this. I'm going to do it what I see as the most efficient way. What I usually find is if you've got a natural log minus a natural log, it's best to combine them. Okay, so I'm going to do that now. So I've got natural log of v of t over v naught equals negative bt over m. We're almost done. Is everybody good?
Yes.
All right, so let's see. I'm trying to solve for v of t. How do I get rid of the natural log?
E to the negative
Take both sides to the e power, right? So if I raise this to the e, the natural log goes away. So I get v of t over v naught equals e to the negative bt over m. Oh, cool. So now I'm done. V of t is v naught times e to the negative bt over m. There you go. That was question number 2. I am sorry that sucks so bad, but it's a thing you gotta know. Aren't you glad you signed up for this class? It seemed like you hit it at the time. Now I hate you, Mr. Hacker. All right. Is everybody good up to here?
Wait, so it's proportional, it's going to be a natural log?
Not always. Often.
Yeah, it would be always.
I guess so. Well, it depends on the other forces, is why I'm hesitating.
Oh.
But I think you can say that. All right. Is everybody good up to here? Is anybody not good up to here? All right. So now let's go back and get questions 3, 4, and 5. Question 3 says, how long will it take to get to a certain velocity, right? How much time does it take to get to a velocity vf, right? So here's my recommendation. You want to solve for t, right? Solve that for t. The question wants to know, how much time does it take to get to vf? Right? So this is your vf, solve for t. So 3 becomes t equals, well, how do I get rid of the negative b over m? Multiply by negative m over b. So negative m over b times the natural log of vf over v naught. There you go. That's number 3. Yes, sir.
The problem's always going to be like no numbers.
Yeah, because they hate you. Well, all of them.
So
Bad
basically
at you.
what our answers will be like, I'm gonna be like, okay, you start at like a year second.
Yep, this is what they're going to look like.
Ew.
Yes, I know. Ew, I agree. These are gross.
Would this be more of an FRQ or a multiple choice?
Oh, totally FRQ. Yeah, this is like, yeah, you'd have, so the FRQs, there's 3 of them, you get 45 minutes, so you'd have, 15 minutes for time. No problem with this. All right, everybody good with number 3?
What are they usually? Is that like a good question?
Sorry?
Like, can you narrow down to like...
Narrow what down?
Like the FRQ is what usually appears on them? Or is it so involved?
Yeah, we'll talk about that a little bit more once we get to the actual practice test, which we'll do some of, I think, next week. If everything goes according to plan. Okay, problem number 4 says, when will it stop? Right? How much time will it take before the velocity becomes 0? What value of t makes this mess 0?
0. No.
E to the 0, that doesn't even work, does it? Because it was moving at the beginning. So that's a good check. Check it out. If I put 0 in for t, what's e to the 0?
1.
So what do we get?
E is 0.
You get v naught. Hooray, that works. At time 0, our velocity is v naught, right? And then as t gets bigger, this is e to the negative something, right? So this gets closer and closer to 0. Does it ever get to 0? No. When does it stop? Never. All right? If you don't like stuff like this, you all have a graphing calculator that you're allowed to use. Use it. Graph the function. All right? Our function was v of t equals negative, no, it wasn't negative, sorry. V naught e to the negative b over m v naught? No, bt over m? There we go. All right, so I made up some BS numbers for these. I chose, when I did this, where's my sheet? If you want to write down the numbers I used v naught is 10, b is 2, and m is 5 to get this equation. Oh, why does this hate me? So v of t is v naught, which I just said was 10, times e to the negative b over m is going to be 0.4, and I got to use x instead of t because of the way Desmos is set up. So that's what the graph of the velocity looks like. Cool. And notice at time 0, my velocity is 10, which is what I chose for my v naught. Okay? And as time goes on, my velocity approaches to 0 but never gets to it. Now, here's the wild thing. Read question 5.
How far?
How far will it go? Well, it never stops.
And until it's
To the edge of the space station.
So how far will it go? Weirdly, no.
it travels over far.
Weirdly, it travels a finite distance, even though it never stops.
Well, it's
Oh,
caught.
eventually it gets so slow, it's like.
All right? So, one thing you can do to prove this is use your calculator and take the integral of this, right? Why? Why would taking an integral help? Because the integral of velocity is displacement, right? Oh, and you know what? Actually, the integral is not hard to take. It is not a lie. It is not a lie. Because what's the derivative of e to the x?
E to the x.
What's the integral of e to the x? Oh, we're taking the integral of e to the x. Displacement is the integral from 0 to time t of, oh, I'm going to pull the v naught out, e to the negative bt over m dt. So what would I have to take the derivative of to get this? Well, if I take the derivative of this, I'm going to get this, but chain rule, I've got to multiply by negative b over m, right? So you got to get rid of it, you got to put in a negative m over b, right? Oops, sorry, I didn't flip it. M over b. Why am I dumb? M over b, e to the negative bt over m. T is the variable, so that's why you don't worry about the t. So do you guys agree if I take the derivative of this, won't I get that?
Sure.
Well, because when you take the derivative of e to the negative, remember, t is our variable.
Yeah.
So like, the derivative of e to the x is e to the x, right? What's the derivative of e to the 2x? 2 times e to the x, right? So to get rid of the 2, you'd have to multiply by a half, right? That's what I did over here. I've got b over m, so I multiplied by m over b. Good? Adriana, and then
This
Weston?
might be kind of snarky, but I also am like kind of serious. When it's saying like how far will the apple travel, it will tell you in the question that it's time to another astronaut. Isn't it just like?
I gotcha.
Like,
Yeah, you're right. I could have worded that better. You're right. You're right. Okay. No, you're 100% right. You're 100% right. Weston?
Why do you have delta x equals v naught?
I don't. I have delta x equals the integral of v of t. This, here, I skipped a line.
You just pull out a constant.
My stupid head is in the way. And v naught is the constant, so I just pulled out the constant. All right, everybody good? Michael?
Would you have to solve the integral for step 5? Or for,
Yeah. So honestly, this part of this problem is hard, but the only reason I wanted to show it to you is that it's wild that it never stops moving, but there's a finite distance that it travels, honestly. So I'm being a little greedy here, like you probably would get a problem like this sometimes. But let's finish it. We're almost done. Yeah.
You can. I'll ask after.
Okay. All right. So then we evaluate between 0 and t. So plug in your numbers. So, oh, wait a minute. Let's let t go to infinity. That's, sorry, how I wrote it in my notes, and I didn't write it here. Right? Because isn't that the idea? We want to go to infinity, right? And, yeah, sorry. All right. So, what's e to the negative infinity?
0.
0. Oh, okay. So I'm going to get 0 minus negative v naught m over b times e to the 0. What's e to the 0? 1. Oh. So here's my answer, VOM over B. That's how far it goes. All right, I'll show you a graphical representation of this in a second after I answer Sean's question. Yeah.
So mathematically, I see that it makes sense, but conceptually, it still doesn't make any sense.
Yeah, so what's happening is it's slowing down. This is going to be worded terribly because there's nothing mathematically good about what I'm about to say. But I think it'll help you process it. The velocity is slowing down faster than time is increasing.
Yeah,
That's a crappy sentence, but the idea is it's the velocity is slowing down very, 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 very quickly, but it never gets to zero. So I don't know if this will help at all. If you graph the displacement, so I'm going to add in another graph here. So the derivative of this mass is, sorry, the integral of this mass, the integral of this, sorry, I'm pointing at my computer screen. The integral of this is negative, what would it be? So if I took the derivative, I'd get 4. So I need 40, is that right? What's 40 times 0.4? Not 10. So what number times 0.4 is 10? 10 divided by 0.4 is 25? 25, final answer. I think that's right. E to the negative 0.4x. So that's what the derivative of this function looks like, plus c. Well, look, what's our position at time 0? Oh, this is not right. Hold on. Sorry, guys. So much for getting through 2 examples. What do we need? VOM over B. So VOM 50 over B, that's 25. Oh yeah, this works. I'm sorry. Yeah. So what's our position at time 0, you guys? I haven't thrown it yet. What's the position? 0. Oh, but my graph shows the position at time 0 being negative 25. So let's add 25 to shift this thing up so it starts at 0. So now here are my 2 graphs. So look, the red graph is the velocity slowing down. The black graph is the position. It starts at 0 and then it flattens out. So the idea though is this slope never hits 0. It just gets super, super close to 0.
So at that point, it's like the distance it is traveling.
Becomes
So
infinitesimal, yeah. It's always moving, but it's never going to pass a position of, in this case, 25 meters. Follow? All right, that took way longer than I hoped it would. So, all right, so it doesn't make sense to go through another example because we'd be jamming through it. But, so let's pause and process what we just did. Okay? And then at some point we're going to have to do one more example where there's gravity. Okay? Which honestly doesn't make it much harder. Or really any harder. All right. All right, so.
Wait, did you cut?
All right, so again, you guys, the process is always the same. You're always going to be given some variable force, where the value of the force depends on the velocity. So make your free body diagram and write a net force equals net force statement. Okay? Then replace your acceleration with dv dt. That's your differential equation. That's 1 or 2 points on the test. Cool? All right, then rearrange. Get all of your V's and dV's on one side, T's, dT's, and constants on the other side. Cool? When you take your integral, you think about your bounds. Your time will, I think, always go from 0 to t. And then your velocity always goes from your starting velocity up to v of t, right? Then integrate and solve for v of t, which is calculus and algebra wizardry. Hence the hats and stuff. I think that's it. Does that make any sense at all? Okay. So my recommendation is if you've got time, maybe tomorrow on a half day, why don't you try try number 2. Try number 2. I guess it doesn't matter because we're probably not. Well,
I've been trying number 2, but I'm so fast.
Try number 2, and we'll go over it. If not this week, definitely early next week. So.
And then
All right.
multiple choice.
No, nothing from 16 is due until. Oh, I gotcha. What's due tomorrow? Tomorrow's a work day. You got 20 minutes. Use it. I don't think it makes sense for us to try to. All right. So the problems from 15-2, all of 15-2 is due on Friday. I guess I don't know. Does it make sense to make a multiple choice due tomorrow?
Yeah.
Or salad games tonight.
How many multiple choice problems are there? Yeah, let's do that. Let's make multiple choice due tomorrow. It's 13 problems. Do your best.
That's 13.
Hey, you can look.
You guys know who I am. It's fine. Do your best. I'm not going to check it. There's only 20 minutes. Going over the problems. Get up in the morning, dude.
Wait, you got it.
Yes, a little bit. Oh, okay, gotcha. All right. Thanks. Have a good day! John, also, where'd you go? No, Papa John. No, Papa John. He's gone.
What are you gonna say?
I was going to tell him no spoilers.
Oh, wait.
I'd rather see the spoil endgame than
So, Frank and I figured out how, and here's my prediction. Frank and I figured out how Endgame's going to end. Rocket, this is a total prediction. This is based only on me thinking.
Nice.
Rocket Raccoon is going to steal Thanos' arm and the glove in the process.
That'd be really funny, actually.
Right? Because he's always stealing stuff.
Yeah.
How great would it be if the
Oh, no,
Rocket Raccoon stole it?
that would be pretty
I
fun.
don't want Tony to die,
Oh,
but also he's definitely
Who?
Him and Chris
Iron
Evans.
Man.
Um,
I don't want him to just like die.
I see him, Chris Evans.
Thor's making too much money. They're not gonna be.
Thor's got another movie or 2 last time.
Yeah.
well, Chris Evans doesn't want to do it anymore.
Yeah, Chris Evans, I would guess him.
Chris Evans is dying.
Dude.
RBJ would be that, I'm guessing.
Yeah.
And
Oh, I'm still recording. Hey, everybody.
Doesn't die, then
So
it's
Avengers
not like
Endgame
a
comes
true
out tomorrow.
end of the
No, yeah, tomorrow. There you go.
Tomorrow? It was tomorrow.